This is a method to calculate the runtime of recursive algorithms, and it's quite frequently used. So the way so this algorithm is mainly used for recursive algorithms, and we start off by filling in this table. It's pretty simple. So first we start off by drawing out the tree diagram for the given code, and this is the code we're going to try and calculate the runtime for. So we have this Iron Man algorithm, and we have these two recursive calls. So if I were to draw out this diagram, it would just look like my one node, right? I'm going to start off with one node. That would be the first call to Iron Man, and then it's going to pass through this whole thing, and then it's going to call these two I am Iron Man algorithms. So this one node is going to call two nodes of the I am Iron Man algorithm. And then each of these two nodes is again going to pass through this algorithm and call another two executions of the I am Iron Man algorithm. So this one's going to call 2, and this one's going to call 2. And again, each of these nodes would call 2 executions of the algorithm, and each of these nodes will call 2, and so on and so forth until we reach the end of our tree, which is when we reach the base case. Okay, so that's our tree. Next, we calculate the work per node. So in each execution of the I am Iron Man algorithm, we need to calculate the amount of work done by this whole thing. So this is an if statement, and it's going to take constant runtime because this is just a comparison operation. So this is constant runtime. Right. This is just returning 1. It's a constant runtime operation. This print is a constant runtime operation, and we're going to halve 20 by 2 each time, and that's constant runtime. So I guess an important thing to make note of in our tree diagram would have been the input parameter. So we could write the input parameter inside the circle. So we're going to pass in 20 first, and every execution, 20 is going to be halved, and then we're going to call our next recursive algorithm. So if we start off with an input of size n, we're going to get n by 2 called for the next recursive algorithm, and this one again is going to pass in n by 2, right? So this is again n by 2, and this n by 2 is going to be halved because the next time, so this is the part where n by 2 is so n becomes n by 2, and we're going to call I am Iron Man on the new Tony, or the new n. So that's going to just be n by 4. This n by 4, n by 4, n by 4, n by 4, and this is going to be n by 8, and so on and so forth. All of these are n by 8. Okay, and this is just our input into the method. Okay, now let's go back to the work per node. So we just discussed that most of these things are constant runtime. We're going to leave out the recursive calls for now, but we didn't calculate the runtime of this whole loop. This loop is going to loop 3,000 times, but 3,000 is still a constant, so the runtime of this whole loop is again going to be a constant, even though the number 3,000 looks really huge. This is constant runtime. So what is the work done by the I am Iron Man algorithm? We just have constant runtime, and if we add together constant runtimes, it's going to give us another constant. So our runtime for one execution is just going to be constant. So the work per node is going to be a constant, and I'm going to represent the constant by C. Maybe I'm going to change the color of my pen. So the work per node for the first node is C, and irrespective of which node you are at in this particular algorithm, the work per node is always going to be C, because the work doesn't really depend on your input in any way. Okay, so the work per node in my second layer is also going to be C. The work for each of these nodes again is going to be C, and so on and so forth. Now, we're moving on to the number of nodes per layer. In our first layer, we drew out one node, right? In our second layer, we drew out 2 nodes, then we drew out 4 nodes, and 8 nodes, and so on and so forth. So 1 is just the same thing as 2 to the power of 0, 2 is the same thing as 2 to the power of 1, 4 is the same thing as 2 to the power of 2, 8 is the same thing as 2 to the power of 3, and this will go on till the last layer. And we notice a pattern here, and because of this pattern, we can write out our last layer as 2 to the power of the height of the tree. And we're not sure what the height of the tree is yet. Well, we'll come to that part a little later. So 2 to the power of height of the tree will equal something. Right? Okay, so these are our nodes per layer. We've written them out. Right? Next, we have the cost. Okay, so before we come to the cost, I guess it's nice to just run over how we know the height of the tree. So this is something you could follow over here. For a tree which starts off with n, and then there's a recursive call with an input of size n minus 1, and then n minus 2, n minus 3, and so on and so forth, we could say that the height is n. And that's just because of our input size. So n minus 1, n minus 2, n minus 3, all the way to perhaps whatever our base case is. So it was 1 in this case. This would count as n. The height of the tree would be n, because you have 1, 2, 3, 4, 5, etc., all the way to n. Okay. And for something like this, the height of this tree, so we have n as our first input parameter, and then our next recursive call takes in an input of size n divided by 2, and then n divided by 4, n divided by 8, so on and so forth. So the height of this tree is going to be log base 2n. And it's a very common pattern when you divide n by 2, or your input by 2. You get the height of the tree as log base 2n. Okay, so that's our height of the tree. That's a really important concept, and these are the 2 most common occurrences you'll be seeing in 61a, 61b, I think cs172, but yeah. All right, and the branching factor, that's also another important concept. The branching factor is just the number of recursive calls made within my function. So this is our first node. It's attached to 1 node, and this is also attached to 1 node. This is also attached to 1 node, so on and so forth. So our branching factor is 1 because it's attached to just 1 node. Over here, each node is attached to 2 children nodes. Right, so this node is attached to 2 children nodes. This node is attached to 2 children nodes, and so on and so forth. So the branching factor is 2. The branching factor is important because you could use it to calculate the number of nodes in the last layer, as we're going to be doing here. So there's a formula which states that the branching factor to the power of the tree height equals to the number of nodes in the last layer. And in general, the branching factor to the power of layer number equals to the number of nodes in that particular layer. So in this case, 2 to the power of height of the tree would be the number of nodes in the last layer, and we know the height of this particular tree, since the pattern is n, then n by 2, n by 4, the height is going to be n. Oh, sorry, log base 2n. Yeah. So it'll be 2, oh no, it'll be 2 to the power of log base 2 of n. And an important math concept is that 2 to the power of log base 2 of anything is just equal to that particular value. So 2 to the power of log base 2 of a is equal to a. And you might have seen this as e to the power of ln a equals to a. That's a more common occurrence, I guess, in math class, but this follows the same concept. So 2 to the power of log base 2 of n is just equal to n. Okay. So that's the number of nodes in our last layer. I've also noted down a few other important formulas which you're going to be using now to calculate the cost for each layer. Now, the cost is just the work per node into or multiplied by the number of nodes per layer. And in our 0th layer, the cost is just going to be the nodes per layer, which is 1, multiplied by the work in the work per node. The work per node, which is c. In the next layer, the work per node is c. That's going to be multiplied by the number of nodes in that layer, which is 2. And we're going to be doing this for all our layers. Right? So we're going to get this 4 into c, 8 into c, and for our last layer, it's just going to be n into c. All right. So after we've calculated the cost, we need to add the costs for all the layers together to get the final runtime of the whole algorithm. And if we add together all these values, it's going to look like this. So it's going to be 1 into c plus 2 into c plus 4 into c plus 8 into c, etc., all the way to n into c. Now this is the same thing as taking c in common and 1 plus 2 plus 4, etc., all the way to n. Now we could write out these values as powers of 2. So that's c into 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3, etc. All the way to 2 to the power of log base 2 of n. This might make it easier to see that what we have right here is the sum of the first n terms of the geometric series. We could write out this sum using this formula. So the sum of the first n terms in the geometric series is a into 1 minus r to the power of n over 1 minus r. Right? So this is an important formula. But something I noticed is that the sum of terms in a geometric series is of the order of big O of the last term. So that's a really cool fact. That means since this is a geometric series and it's an increasing geometric series, I can say that this whole thing can be written out as big O of the last term, which is 2 to the power of log base 2 of n, which was n. Okay, and that's with big O notation. It's just a fact. You could write it out as, you could write out the whole sum as big O of the last term. Okay, so this is of the order of big O of the last term, and since this is just a constant, this whole thing is just big O of Cn, and C is a constant, so it's big O of n. Because constants don't matter when you're considering big O runtime, or runtime in general, I think. If you're considering big theta, big O, or omega runtime, yeah. Constants don't matter. So this should be our final answer. Big O of n is the runtime of this algorithm. Yeah, so I guess this is a helpful note on how to do this, and when you're solving it, following this method should work. Yeah, thanks for watching.